In this video, we will be looking at how to solve trig equations when factoring is involved and some basic trig identities are involved. So our first example is going to have a common factor. So we're going to solve tan x times cos squared x equals tan x for the interval of 0 to 2 pi. So I noticed that I have two terms here and they both have a tan x in common, which is going to guide me into bringing that tan x over. So that I have tan x times cos squared x minus tan x equals 0. And once I do that, I notice that there is a common factor of tan x. So when we factor out that tan x from the first term, we're left with cos squared x. And when I factor it out from the second, I'm left with minus 1. And now I'm going to set each of my factors, so each of my brackets equal to 0, and solve the individual equations. So that means I have tan x equals 0. And I have cos squared x minus 1 equals 0. So I'll start off by solving tan x equals 0, and I can think back to what that base function of tan looks like, or I can use that fake special triangle with the 0 and pi over 2. I personally prefer thinking of the base function. Now, as a reminder, when we graphed tan x, we thought of it as sine x over cos x, and our x-intercepts occur when the numerator, so sine x, is equal to 0. Well, sine is equal to 0 at 0, pi, and 2 pi. And honestly, that's all I really need for my graph. I don't even need the rest, but just as a refresher, my vertical asymptotes came from when the denominator, so cos x, when cos x was equal to 0. And that would be at pi over 2 and 3 pi over 2. And then I can do my graph like this. But I really only needed my zeros here because we are solving the equation tan x equals 0. And the y values are equal to 0 at 0, pi, and 2 pi within the interval that was given to me. Now I'm going to go ahead and solve cos squared x minus 1 equals 0. I'll start off by bringing that 1 over to the other side, and then I'm going to square root both sides so that I have cos x equals plus or minus 1. And when I see 1 and negative 1, I'm thinking about the max and mins of that base function. So once again, I'm going to think of the base function, and this time for cos. And we know cos is at a maximum at the start and the end, so that's at 0 and at 2 pi. And it's at the minimum halfway at pi. So it's actually the exact same answers as with tan x. So there we go. For this first equation, x is equal to 0, pi, and 2 pi for the left side and the right side to match within the given interval. Let's try another example. This time the focus is on trinomial factoring. So the reason I'm thinking of this as trinomial factoring is because I see it as a bit like quadratic. We see that sine squared x, then we have a sine x term, and then we have a constant as if we had x squared x constant, where we would do crisscross or the Australian method or decomposition, whichever you prefer. Now you can factor your trinomial right away as is, but I will show you a way that will remove the signs temporarily, and you can do whichever you prefer. Now, first of all, before we factor, just like with a quadratic, you have to ensure that one side is equal to 0, which it is. And now I'm just going to do a little swap to make my life easier. So let's say A, or whatever letter you want. Let's say A represents sine x, so that we have 3a squared minus a minus 2 equals 0. we're taking the trig out of it, and now we can factor as if we were in grade 10. So 3a times a, and then 2 times 1, and I think the 1 should be negative. And for my check, 2a, negative 3a, those add up to the middle term of negative a, so this is perfect. And here is my factored equation. Okay, but of course, this isn't about a, it's about sine. So now I'm going to go back and replace the a's with sine x to get back to that trig equation I wanted to solve. So what I'm actually solving is 3 times sine x plus 2 in one bracket, and then sine x minus 1 in the other. And now I will branch out and solve the individual equations. Now, if you don't need this little let statement here and you can go straight to your crisscross or whatever method, that's perfectly fine. And I'll just show you on the side here how we can do it like that as well. So just like with crisscross, two terms that multiply to 3 sine squared x, well, 3 sine x and 1 sine x. And then two terms that multiply to negative 2, and this is what my check will have to be. Well, again, 2 and negative 1. That way I have 2 sine x and then negative 3 sine x. And when I collect those, I get the negative sine x from the middle. So either way is perfectly fine. Okay, now that it is factored, let's solve the individual equations. 3 sine x plus 2 equals 0, and then sine x minus 1 equals 0. I'm going to start with the second one because it is a little quicker. When I bring that negative 1 over, I'm just solving when sine x equals 1. So I'm going to draw my base function here because 1 is the maximum. And this is the value I'm looking for. And I know on the sine graph, that's at pi over 2 because every key point occurs pi over 2 radians apart. So there's one solution from that first equation. So I'll just keep that in mind. Now I'll go back to the other one. When I isolate for sine x, I know I'm going to bring the 2 over, it's going to turn negative, and then I'd have to divide out that coefficient of 3. So I just did 2 steps in one, and I'm solving sine x equals negative 2/3. And this is not part of a special triangle, so I need to go to my calculator here and take the sine inverse of the positive ratio. Remember, we're using the positive ratio because it's an acute angle. Acute angles are in quadrant 1, and all of our ratios are positive in quadrant 1. So I need to take the sine inverse of the positive ratio. And when I do that, I get 0.73. And we were given a negative ratio for sine, and sine is negative in quadrant 3 and quadrant 4. So I'm going to do my modifications to get my two angles. In quadrant 3, we're past pi, so pi plus 0.73, and that's approximately 3.87. And in quadrant 4, we're almost at 2 pi, but not quite, so 2 pi minus 0.73, and I get 5.55. So there's another two answers. And I will just finish this question off by listing all of my answers. Therefore, x equals pi over 2, 3.87, and 5.55. And there we go, a little bit of crisscross with trig. Our next example is going to involve that same type of factoring, but this time we're going to combine it with an identity. And you will see in this example here that I have cos squared x and sine x. And there's a fantastic identity that can remove cos squared x and turn it into something about sine instead. And I'm going to refresh on that identity just above, right here. And it comes from the Pythagorean identity. The Pythagorean identity is sine squared x plus cos squared x equals 1. And remember, this identity also gives you another 2 when you just rearrange it. So let's say I bring cos squared x over to the other side. I also have this identity. Cos squared x is equivalent to 1 minus sine squared x. So how about we do that swap right now? So I'll have negative 10, and then I'll open up a bracket for 1 minus sine squared x, and then I'll write the rest. And this was a perfect move because now everything is about sine. I will do a little bit of distribution here and cleaning up to get it into its proper trinomial format, but otherwise, I'm almost ready to factor. And the original problem I had is now gone. Okay, brackets are gone. Now I'm just going to clean up here. So 10 sine squared x minus 3 sine x, and then collect the constants, and we have minus 1. And now we can factor. You can just jump straight to your crisscross, or if you'd like to replace that sine x with a more basic letter, more than welcome to. I'll show it that way. I do like going straight to the crisscross though, if I'm being honest, but here we are. So when I do my crisscross here, thinking 5a times 2a, it is going to have to be 1 times 1 here, but this 1 would be better as my negative option. That way I have negative 5a, positive 2a, and then here is my factored form. 5a plus 1, 2a minus 1 equals 0. And now I can of course go back to turning this into a trig equation. So 5 sine x plus 1 in one bracket, 2 sine x minus 1 in the other bracket. And now we can branch out to actually solve this. So we need to set 5 sine x plus 1 equal to 0 and 2 sine x minus 1 equal to 0. And let's isolate for sine x. Bring the 1 over and divide by 5. Bring the negative 1 over and divide by 2. These are the two equations that we're actually going to solve for here. And we're going to have 2 answers in each, so we'll have 4 in total within this interval. So I'm just going to solve one at a time here. For sine x equals negative 1/2, my alpha is going to be sine inverse of positive 1/5. That's going to give us an alpha of approximately 0.2 or 0.20. And because we were given a negative ratio here, we know we're going to be in quadrant 3 and 4. So in our quadrant 3, x is going to be pi plus 0.2, and that's approximately 3.34. In quadrant 4, we're doing 2 pi subtract 0.2, and that's approximately 6.08. And now we can go to our other equation, sine x equals 1/2. This is actually from our special triangle. It's that equilateral triangle that was cut in half. And if I want opposite to be 1 and hypotenuse to be 2, this should be my special triangle or special angle, and it's going to be pi over 6, or that 30-degree angle. So alpha is pi over 6, no calculator here, and our ratio is positive, so we're in quadrant 1 and quadrant 2. So one of our x's is just pi over 6, and the other one is pi subtract pi over 6. Get yourself that common denominator, and there's your other option. So we have pi over 6 in quadrant 1, 5 pi over 6 in quadrant 2, 3.34 in quadrant 3, and 6.08 in quadrant 4. And I will list those out to conclude my answer here. And I am writing my values in numerical order. And there we are. We used an identity to make everything about sign. We did a crisscross factoring, and we solved each individual equation that came from the brackets. Let's try one more example here. So we have secant squared x plus 5 tan x equals -2. This is also going to be a variation of the Pythagorean identity. And I'm going to be honest with you, this is an identity that I don't memorize, but I can grab it from the original Pythagorean identity. So I'm going to show you my little shortcut so that I don't waste brain space memorizing. So here's the Pythagorean identity I know. We can divide this identity, divide each component by either sine or cos to get something to sub in or to get another identity out of it. Because I see I have secant in here, I'm going to choose to divide by cos. And let's see what happens when I do that. I'm going to divide everything by cos squared x. And when I have sine squared x over cos squared x, that's tan squared x. Cos squared x over cos squared x is 1. And then 1 over cos squared x is the secant squared x. And here is another identity. Now, of course, if you have it memorized, you don't have to worry about this. I just wanted to show you a nice little way to get other identities if you forget them. But now I know that secant is equivalent to tan squared x plus 1. So I can go in and swap that in so that everything is about tan. So I'll have tan squared x plus 1, and then the remainder, so plus 5 tan x equals -2. And now just clean this up so that it's ready to go for that trinomial factoring. Tan squared x plus 5 tan x. I'm going to bring the -2 over because just like with a quadratic, one side has to be equal to 0 the minute I see that exponent of 2 there. So when I bring it over, it's going to be plus 2. And when it collects with the plus 1, we have plus 3. Now, if I try to factor this, I wouldn't get anywhere. Even if I replace this with, let's say I had a squared plus 5a plus 3 equals 0. And I said, let a equal tan x. I cannot factor this. A times a, 3 times 1. There are no other options. 3a and 1a add up to 4a. But we know from grade 10 that if something's not factorable, we can do quadratic formula. So we're going to do quadratic formula here. And I will just remind us of what that quadratic formula is. Although by now it should be ingrained in our brains. But here we go. Let's do our quadratic formula. I'll do it from this simplified version, although I can also go straight from my tan version. But here we go. A equals -b, so -5 plus or minus b squared, so 5 squared minus 4 times a is 1 times c is 3. All over 2 times 1, because remember, there's an invisible 1 in front of that a squared. And now we clean up. The part under the square root, 5 squared minus 4 times 3 is 13. The denominator is 2. This will not give us an exact value, so I will just get my 2 options for a. So I'm going to do -5 plus the square root of 13, all divided by 2. And when I do that, I get approximately -0.697. And when I do the subtraction version, I get approximately -4.303. Now those are that's what a is equal to. But we know that a is equal to tan x. So I'll replace each of these values with tan x. So tan x equals -0.697. We're going to solve that. And tan x equals -4.303. And both of these little equations definitely not related to our special triangles. So I'm going to find my alpha with a quick tan inverse of the positive version. So in this first equation, alpha is approximately 0.61. And we had a negative ratio, and tan is negative in quadrant 2 and quadrant 4. So in quadrant 2, x is equal to pi minus 0.61, and that's approximately 2.53. In quadrant 4, x is equal to 2 pi minus 0.61, and that's approximately 5.67. So there's two answers. Let's go find another two answers from our other bracket. Tan inverse of 4.303, and this time for alpha I get approximately 1.34. Same quadrants, quadrant 2 and 4, because I have another negative ratio here. So in quadrant 2, pi minus 1.34, and I get approximately 1.8. And in quadrant 4, I'm doing 2 pi minus my alpha, and I get approximately 4.94. And now I just have to list them all out to conclude my solution here. So therefore x is equal to, and I'm just going to go in order here. So the 1.8, then the 2.53, then the 4.94, and the 5.67. And there we are. Now we have a trig equation with the quadratic formula. But once you do, just like with the other examples, once you did your factoring or your quadratic equation, it always went back to some sort of basic equation. Yeah, you had to solve two basic equations, but exact same style of find your alpha, use your quadrants, get your angles.